So it's my pleasure to introduce our speaker today, Dr. Gregory Forcherio from the Naval Surface Warfare Center in Crane, Indiana. So actually Greg here is with a team of other scientists and also the director of Crane, Indiana. And so he's actually going to talk about research being done at Crane and research in particular being done at the Electro-Optic Technology division at their organization. So I just want to say a few things about Greg. His research focuses on disruptive electro-optic and IR technologies for multi-domain expeditionary operations based on resonance surface optics using plasmonics, metamaterials, and low-dimensional materials. In particular, I think what he'll talk about today is using metamaterials to advance IR imaging. So he was formerly a chemical engineer in sensors and electronic devices at the U.S. Army Research Laboratory. He's been awarded many academic and research distinctions, including the ORISE Postdoctoral Research Fellowship and an NSF Graduate Research Fellowship. He did his PhD at the University of Arkansas. He received his BS from Southeast Missouri State University. And he is also very active in the scientific community. He's part of ACS, MRS, SPIE, ECS, OSA, and the Network for Computational Nanotechnology. He's done a lot of work initiating outreach activities to enrich STEM as well. So it's really been a pleasure meeting you and your colleagues today, and I look forward to hearing about the research you guys do at Crane. So thank you very much for listening.
Thanks, Dal, for having us. I really appreciate the platform for letting me come talk about some of my work today. It's been quite a while since I've gotten to have these talks. I used to be a regular on this kind of circuit going around the universities, but for a couple of years that's been hard to come by, so just appreciate the invitation. So today I will talk about some of our work at Crane, kind of rebuilding infrared vision systems from the ground up, starting with new materials to overcome some of the fundamental challenges that just seem to keep popping up in the infrared vision community. So a little bit about Crane first. I'm sure a lot of you in the audience have never heard of Crane, don't really know a lot about Crane. And so here's a general map of the Naval Research and Development establishment. And you'll notice we're an obvious outlier, landlocked in the middle of the country, the third largest naval base in the world by land mass. So that's a little fun fact that we like to shout out there. But we are particularly focused in three main domain areas that will be all distinct from maybe some of our sister organizations you may have heard of. Everywhere down here in the San Diego region, like Niway Pacific. You may have seen some work coming out of maybe perhaps Carter Rock or Dahlgren out in the DC greater area, Panama City. At Crane, Indiana, in the landlocked regime, we're kind of focused on three primary thrust areas, and one that is in support of the Trident missile system, all the microelectronics reliability, radiation effects, etc., that support those strategic systems, electronic spectrum warfare, and where I'm come from is the Expeditionary Warfare Group, where we do anything from foot mount type stuff, ground-based operations. We have about $3 billion moving through our base annually. A lot of that in hardware, repair, etc. We're about 65% scientists, engineers. Here's a breakdown of doctorate, masters, and bachelors. Doctorates growing ever rapidly every single year, so we have a high interest in recruiting high-level advanced degrees, masters through PhD to come to Crane, build up new research portfolios that we can help use to support these three main mission areas. Within expeditionary warfare in particular, I work in the Electro-Optics Technology division, and there we have a pretty wide variety of operations and everything that's supporting these technologies, from the basic research portfolio that I'm primarily involved in, everything up through requirements definitions, test and evaluation of systems, acquisition, engineering support, field, lifetime sustainment, etc. So we do the full life cycle support for all of these infrared sensors in airborne, maritime, and of course ground-based EOS systems, doing intelligence, surveillance, reconnaissance, targeting, security sensors, missile targeting, etc. All comes through our division. I have a few unique test capabilities that we like like to leverage, including trying to invite some certain academic partners to come use and bolster some systems they're working on in their lab. This is a picture of our main building, the Electro-Optics Test and Experimentation Complex. Of particular notice, you notice the large tower. That's where we can do a lot of on-site test and evaluation of these types of infrared systems. After we build them down on our ground floor, do any repairs, we can send them right up the freight elevator and go test and make sure that they work. Have access to bar targets characterization at 1-4 kilometers, full outdoor clearance for class 3, class 4 laser, fly drones out of it. You have immediate access to a lake for water-based scenes, forest, long distance ranging, water towers, etc. If there's nothing we can get done there, we have access to a nearby Lake Glendora. It's about an hour and a half to the northwest. It's a man-made lake where you can have everything to you can fly drone swarms out there. You can underwater munitions, detonations, etc. It's kind of a little playground for us that we have access to, and that is certainly unique. And if you have anything on the small arms side, we have an underground test tunnel with full night vision test environment, salt, fog, environmental conditions that we can controllably test and do there for ballistics, etc. On my team, we call ourselves the Science and Technology branch. So you might see the term S&T pop up a few times throughout these slides. We're a team of about 16, and we're primarily focused, again, on the really low TRL level, more conceptual ideas and trying to get those out to the field, try to accelerate those new types of technologies and concepts to fieldable products. We have 16 of us, about almost half PhDs, with backgrounds anywhere from optics, semiconductor physics, computer science, chemistry, EE, ME. So it's a very interdisciplinary group. It takes that type of background to tackle a lot of these really complex problems. It's not as simple as just building a sensor. You might be having on a gimbal. You have to have an ME, do all those appropriate calibrations, maybe build some novel PCB boards for controls, program all the GUIs, etc. We have visiting professors as part of our team from Vanderbilt, Michigan Tech. We have some smart scholars that are actually Crane employees out at the universities pursuing their advanced degrees that are directly on our team that will return to us and take some of that more cutting-edge academia concepts and bring them into the lab. We have access, drone, robotics prototyping, 3D printers for quick assembly of novel optical housings, ruggedization of optics, etc., high-energy lasers, ultra-high vacuum coatings type lab, and building up some new capabilities in focal plane array testing and characterization that we're building up right now. And then in terms of the actual role that we're playing and what we're trying to achieve is just pretty simply put, we're looking for better performance sensors that are smarter and assured use. And I'm going to talk about two of these areas today that my portfolio is directly tailored towards. And so, again, that is where it comes up, where we're going to build up those new capabilities starting from the ground up at the materials level. So I think a lot of this slide's contents kind of go without saying, given the audience of this particular college. But for anyone in the audience that maybe is earlier on in their education, hasn't quite gotten to the level of infrared yet, just a brief recap is that we like to use the infrared as something of a sixth sense to allow us to see the world in new ways, whether that be new objects, new natural phenomena. Things don't necessarily appear in the infrared that were readily conceivable by our naked eye, and so it allows us to do new types of ways for threat detection, surveillance, etc. And we look at all these different bands, both in the shortwave infrared, midwave infrared, longwave infrared. Each one's a little unique in how they can manifest this information. Here's a simulated scene of a mountain where you can tell each novel infrared band can give you access to different types of background contrasts, different phenomenology will just appear and pop out of these imagery different. It's being able to tailor your hardware to look at these different types of scenes and the different bands to get the information that we want to keep our soldiers safe. So what do we use them for? Now, obviously in the military, touched on this a little bit, everything from night vision, threat detection, surveillance, ballistic guidance, warning. But even in astronomy and climatology, the infrared atmospheric sounders, you do geospatial intelligence of, for example, CO2 concentration in our atmosphere evolving over time. You put these up on the Hubble and James Webb telescopes, but even in the civilian and commercial realm, everything from search and rescue, home energy audits. So, an image you might see if you ever purchased a home of the guy walking around with one of these, looking at thermal leaks at your windows and your doors, trying to improve the insulation, things like that. And they're even making our way into our driver assistance systems more and more. Every single year, as they come out with new models and all those different features. In the DoD in particular, we're mostly interested in accessing the mid and long wave bands, particularly because they let us see through better through fog, dust, and haze. So that is our particular interest. So normally you'd be denied visibility in these kinds of degraded environments, whether that's the fog, dust, and by incorporating a mid-wave sensor, and for example, this rifle telescope, you can see the threats very obviously through these degraded environments. So aspect one that my portfolio tries to tackle is one, we're going to focus on better focal plane array material platforms, because we need these types of sensors fielded prolifically on lots of different platforms. And unfortunately, they're either too big, power hungry, or expensive to field in all the places that we want to put them. And so we want to develop a new focal plane array material system, preferably silicon compatible, that you could economically make these thermal sensors and put them everywhere you want to go and reduce, or at least potentially even remove, all the needed cooling infrastructure needed to image. And that'll make them more compact and more power efficient. And currently in midwave, that does not exist. So this chart is a little dated, but it still holds up pretty well even today. You'll notice this red circle up here. There's no existing focal plane array technologies that operate at room temperature, 300 Kelvin, tailored for the 3 to 5 micron band. And so this presents us an opportunity. Obviously, thermal imaging sensors have been around a long time, and the fact that we have still yet to fill in this bubble tells us that we need to find more disruptive material platforms and look outside of the conventional ways that we've built infrared sensors to date. And our vision at Crane is to find these material platforms, probably quantum related, that can allow for lighter, faster imaging, higher signal to noise, and can be more power efficient and key at significantly lower cost. Again, that's where the silicon compatibility comes in. So we have 4 predominant material platforms we've been exploring in this realm for some time. I'm going to talk today a little bit about my work in quantum plasmonics, developing a few different material systems. We have a smart scholar at West Virginia University, Olivia Pavlik, that is exploring heterostructures of graphene and different types of quantum dot stoichiometries to get a midwave response that would all be deposited onto a silicon FPA. Dr. Tim Morgan, who's here with our group today, has a lot of interest in exploiting group 4 ternary alloys that are based on silicon. So doping silicon with things like germanium and tin to get new types of electronic band structures that can provide higher operating temperature, all on a silicon-based platform. And a recent smart scholar that came on board in the last year is Dr. Sammy Koutsaris, who's transitioning some of her grad work at Norfolk State to help identify new types of vial semi-metal candidates that could allow some really novel detection modalities that are not currently available on any existing infrared sensor. But for today, I will talk briefly about some of my work and how to design a plasmonic-based infrared sensor. So for anyone that's not familiar with surface plasmon resonance, it's effectively just a way on a nanoscale structure to absorb or scatter electromagnetic energy in a controllable way and potentially even generate these energetically hot carriers. So this technology in of itself is nothing new. It's been around since the mid-1800s, dating back to Faraday, who first was able to find a way to suspend colloidal gold in a beaker. Still sits on a shelf today, stable after more than 170 years. And what they notice is obviously this is not gold. So gold at these dimensions is not actually what you perceive as gold. So at the nanoscale, colors change, and that is because of this surface plasmon resonance property. So little spheres like Faraday made back then will absorb all your green light. You're left with red and some blue. It gives off this weird pinkish purple hue in the quasi-static limit. So anything about, say, less than 50 nanometers in diameter. And then in the mid-2000s, obviously, colloidal chemistry has come a long way, and they're able to make some nanorods, get some near-infrared response. You have some little triangular platelets. You can get out past the 1,000 nanometer mark. A lot of interest with this initially was to coat solar cells back in the day to try and fully take advantage of that solar spectrum, concentrate it onto a solar cell and boost the efficiency. Spoiler alert, it doesn't work very well, but that was the thought about 15 years ago. And so that's kind of the classical way to look at surface plasmon resonance. More recently, in the last 10 years, you look at this more at the quantum view, where you're no longer just looking at controlling this dipole mode, but you're now looking at the actual temporal evolution of our photocarriers being generated at the energetic level. And what they found is every time you have an absorption event, you can generate these energetically hot carriers. And if you can control, or at least potentially even put an electrical probe in at a certain point in time and extract these carriers out, that could present a new set of physics to make an uncooled infrared sensor, because these do not need cooling. You're not limited by band gap excitation, recombination lifetimes, etc. So that's a hypothesis people have been chasing for at least about 10 years now. And so we want to actually leverage this as a way to transduce infrared photons that are well below any kind of band gap on a silicon-based platform, and use that as a transducer to make electrical signal. So this is basically a 4-step process. So you would deposit some kind of structure. This is a great example from a collaborator of mine at Vanderbilt, Professor Jason Valentine, made a few years back, where he put these little gold-coated structures on the surface of silicon. And so at some point in time, you can put this on here, and it makes a infrared mode available on this material. And so any kind of infrared photon comes in, it's going to excite the surface plasmon resonance on that nanostructure. After tens of femtoseconds, that's going to generate an energetically hot electron-hole pair. And then after that, you got to get it out. So it's got to transport to the surface and inject over a Schottky barrier to get into your semiconductor. Goes into your readout circuit, and then you can do some time integration and actually make an infrared imager. So how do you actually engineer something like this? And so as an example today, I'll show you, this is some work we did with some crosses. So this is a very trivial geometry. Crosses have a unique infrared response because of the long aspect ratio of these structures. And so you have a few variables to play with in this case. You have the arm length, you have the width, in other words, an aspect ratio. You have some thickness of your structure, and you have the spacing when you have a periodic array of these kind of structures organized. And you use some kind of a noble metal material. Those are some of the classical materials for a surface plasmonic system. You can do some, solve Maxwell's equations, look at how much energetic power you're going to absorb at a dipole mode that you engineer to occur in the midwave. Here I'm showing you some geometries that give about a 3.4 or so micron response. You can see it does have some material dependence. It has these nice, beautiful dipole modes. You can spatially map where your carriers are located on your structure, and that can help you understand what exact geometry you need to make this efficient. But then you also have to ask the question of what are the actual energetics of my carriers that I'm exciting. So in the infrared, we have some nice convenient tricks we can play because we're below the inner band threshold of the material. So everything falls nice, free electron gas, parabolic density of states. Works out to some nice analytical formulas. You go above the inner band threshold is maybe a visible type detector and a near infrared type detector. It gets a little more complicated. You got to do some DFT stuff to play with that, but that's something we can look at. And after you know that, you got to make sure you can actually get it to the metal surface. So you have an energetic carrier up here in energy space. You want that to ballistically transport to your surface. You don't want it crashing on other electrons, phonons, because it's going to start to lose kinetic energy, and you're not going to be able to get that carrier out. And so you'll have to do some DFT calculations, figure out what does the electron mean free path of my material. You got to make a library, figure these kinds of things out. You can do some simple stuff. Turns out silver is actually pretty good. Aluminum's pretty lossy, has lots of grain boundaries. You're going to crash into a lot of stuff. And it's not very efficient, but it's doable. And the last part, you got to get them out. So this follows some old classical theory developed by Fowler back in about the 60s of the general photo emission of an electron over some arbitrary energy barrier. So one, you got to have enough energy. Your energy of your carrier's got to be above that Schottky barrier, and it's got to fall within the momentum cone, or in some cases of some tricks you can play with disordered interfaces that are present in any realistic fab device. It's been proposed that you really just need an electronic acceptance state ready to go. In that semiconductor, you can kick it over. We're working on that kind of hypothesis with a smart scholar at Vanderbilt, Scott Criswell. Is tackling that problem right now. So there's some unique other material aspects that can play in the design of this kind of device. You can put all those terms together and make an expression for quantum efficiency. It's the product of obviously one probability of generating a hot carrier times the probability of getting it to the surface times the probability of actually getting it out. You can map your parameter space for your metamaterial absorber, and you can find your hotspot and say, that's what I want to build. That's going to be optimal mid-wave activity for me. In this case, this is about a 1 to 10% quantum efficient device, just to give you some numbers. Unfortunately, there's two key problems that this kind of approach takes. One, this is a really complex graph. It takes a lot of time to generate. And for a very trivial topology here, the design landscape is absolutely immense. This is one data point I have generated. And sure, I've tackled several parameters, made some assumptions, but it's one material combination. It's a very small data point, and it is a lot of work to get to this point. Number two, this actually has two resonance modes, an individual scattering and an individual absorption mode. They're a little bit separated. And if you look at the scattering peak, I've plotted down here, and I've grayed the other ones out just to keep attention away for now. You'll see all these dipole modes in this array, they're all bleeding into one another. In other words, they're all talking to one another. You're shooting in a photon maybe on this guy, this one up here is going to see it. So you've made a good imager, or a good detector, but you have not necessarily made a good imager. And that's a very key point that a lot of people in this community miss. And so quantum efficiency does not really tell you the whole story here. There's other considerations to make an efficient infrared imager. And that kind of plays into the gap in realizing new IR detector materials that we're tackling at Crane. So traditionally, you'd start at the materials level, make some hypotheses of some cool stuff you want to play with, and you do what they call by-hand engineering. You do what I did. As engineers, we're going to make a series of plots varying one parameter, say this one's the best, fix that parameter, move on to the next parameter, say this one's the best, and you're going to keep doing that sequentially. But that's not exactly how this landscape works. And so you'll come up with some kind of design, and you'll say, I think this is good, and then you have this big gap right here. This is iterative prototyping. It's effectively guess and check that you're going to play for years. Say $10 million, make one prototype, and just say, I don't know, maybe it works, maybe it doesn't. I don't really know what to change because I thought I optimized everything. And you don't really even know, even if you do make a good one, you don't really know how it performs. So that's kind of unconnected. There's not a really good life cycle here to go through for the development of these new technologies. So step one is actually you want to move to an intelligent design framework. Leverage new advances in artificial intelligence, machine learning, big data. We have access to an immense amount of data, especially on the material side, that can remove a lot of the guess and check and iterative prototyping that goes on here, and rationally choose something that makes sense, that can do the feedback between the fundamental description and how the electrodynamics behave for certain materials, new physics, and actually building what that single pixel design would be to elicit some kind of optimized response for infrared. Blame Wikipedia. Noted. Thank you. Step number two is actually finding a way to connect them, and that's where we're building up new capabilities in device modeling and simulation. So it's moving from the single pixel designs we usually tackle with our codes and actually starting to simulate the responses of arrays of pixels and understanding their response. And the key here is finding a way to numerically calculate the modulation transfer function of these and use that as an input to connect the single pixel designs to performance, to understand their detection, recognition, and identification performance that we could put on some kind of fieldable system and intelligently inform what material candidates, new physics we're proposing, are actually worthwhile pursuing. So instead of a 30-year endeavor and a lot of hypotheses and a long road, we can knock out candidates at the earlier stages that we know will no longer work. We can do this all numerically and cycle through many different hypotheses in a much shorter amount of time, acquire new technologies faster, and drive this kind of revolution in a more intelligent way. So for anyone that's not familiar with modulation transfer function, it's effectively describing the capability of some kind of imaging system to reproduce contrast variations. Can you actually resolve the different spatial frequencies in a scene adequately to make, understand whether or not you're looking at a block or you're looking at a tank. It's kind of what you're looking at. So this is at a fixed spatial frequency. Here's what it should look like, a series of step functions. And with decreasing MTF values, eventually you get to something like this where you can't even resolve it. It's a big gray blur. Good MTF, you can actually adequately resolve everything. Usually you'd go measure this on a bar target. In places like I showed you in our tower that has bar targets outdoors, and you go look at that for a actual functional system. And it's a convolution of many different components. It's not just the detector focal plane array that I'll talk about today, but it's actually what they call a cascade of many components of your imaging system. We're going to tackle one small portion. We'll move to the others in a little while. So we're tackling this with the Center for Semiconductor Modeling that was initially started out at the Army Research Laboratory. And their idea is effectively to numerically calculate MTF by simulating the impulse response of a single pixel design that is organized in an array. So in a lab, you might do a knife edge technique or some kind of laser speckle measurement to understand the impulse response of some optical element. I think these diagrams are trying to do that for a lens. But we're trying to taking some lessons from that and going into the virtual domain and building a 3x3 array of our whatever pixel design that we want to pursue. And we're trying to numerically construct what that impulse response is for that single pixel by the time it's interacting with others in an array. And so we can do that by taking a beam and sweeping that across a center pixel. And I'll show more in the following slide. But effectively looking at the optical and electrical crosstalk components that drive the response of that single pixel being interrogated by a Gaussian beam. And decoupling that into the appropriate crosstalk contributions so we know where to focus our efforts into understanding how to alter that pixel design to kill out all those electrical and optical crosstalks so we can have a really good MTF before we go to the prototyping investment stages. And so we just recently completed a case study of this, just looking at a very simple mid-wave mercury cadmium telluride design, a simple PN junction is a good starting point. So this is the pixel design. Again, it's just an ion implantation, P-type, into an N-type wafer. Simple PN junction here, probably a bias across it. And we build a 3x3 array over here, take a Gaussian beam at 3 microns and sweep it laterally across that. And we look at all the activity that goes on in the center pixel. Both looking at the photocurrent, so that gives you both the optical and electrical components to that, as well as just looking at the optical generation rates of photocarriers in the center pixel versus that of the entire array. And you'll get this spot scan profile, something that looks like a nice bell curve. So the optical generation rates will have a spot scan profile that looks like this in the red. And by the time you have electrical crosstalk, that's going to widen, it's going to blur out because your center pixel's talking to your neighboring pixels, and you'll get a little bit of a broader talk over there by the time you look at the diffusion of carriers. And if you did take the Fourier transform of these spot scan profiles or impulse responses, you can get a total MTF, and you can begin to break that and decompose that out into the detector hardware itself, as well as its underlying optical electrical crosstalk portions, as well as the fundamental pixel limits, judging by the pixel pitch of your detector. In this case, we have middling performance here for this kind of just exemplar case study here, where the black is our detector hardware, which is limited by this blue curve, which is the electrical crosstalk. So in this case, this is just a simple, again, planar PN junction, and so the diffusion of photocarriers is what's killing our performance, where you see it die out down here at about 90 cycles per millimeter. Optical crosstalk, we're stay at pretty high MTF value. The optical crosstalk is great in this design, but it's really electrical crosstalk that's killing us. And so you could take this information and revisit your single pixel design and begin to implement new strategies. It would be a MESA architecture, some kind of etching or whatever have you, to try electrically isolate these pixels from one another a little bit more to tamper down that diffusion crosstalk problem. And looking forward to the future, we begin to also leverage intelligent design of these crosstalk strategies. And so using AI/ML to look at some of these different parameters in the architecture design to optimize this all the way before we begin to feed that into the performance-based modeling to see How far can I see with it? Is this going to do what my acquisition office wants it to do? Or, they're going to pay me to see a tank at 10 kilometers. Can it actually do that? Make some assumptions with the optics, etc. So that's kind of where we're ultimately going with this. This is a new capability we stood up this year, and we're really excited to kind of see what new designs this leads to. Next level of performance I'm going to give a brief talk about is making our optics themselves smarter. And so one of the current issues we have with tracking algorithms is the fact that they're very power and data intensive, and they really cannot operate at the frame rates that we'd like them to. You need some GPUs to do all that onboard processing. It creates an immense amount of problems in terms of putting this on a fieldable system because of the power requirements, the footprints, so that all the data transfer bandwidth, there's lots of issues there. And so we'd like to somewhat embed processing into the hardware side. And we're going to do this by using dielectric metamaterials to actually do image processing passively at the optics level and kind of pre-process our scenes before they reach the focal plane array themselves. So convolutional neural networks are kind of what form the underlying basis of all of our AI/ML systems, and has really changed our ability to obviously process and process data feeds and going towards decision-ready data. No longer a human interpreting what they think they see in a scene, but we actually want the computer to spit out, go a few levels beyond that and tell it sees this at this coordinate, and cut straight to the action. That's really kind of the dream. And so there's different levels of CNNs of what they can do. You can do everything from classifying this as a cat, localizing where the cat is in the scene, or even doing cluttered environments, trying to distinguish between a cat, dog, duck, or even segmenting the image itself. Do spectral discrimination within this and look at different components, maybe different gas plumes or some other kind of byproduct of what could be extracted from these types of infrared signatures. But if you really break down the architecture of a convolutional neural network, you see it looks like a cascaded system, something like this, where you have a scene coming into your camera and it records this kind of RGB image, feeds it into an algorithm, and it tries to make a decision. Eventually, you can go through all these different layers, which are pretty intensive. This takes about 17 billion floating point operations. And on the back end, hopefully it can tell you it's an Audi A7 if you have the appropriate information. And a key problem here is that if you use a single GPU system, this kind of process for even a rudimentary piece of hardware like a 512 pixel format, which is really low resolution, you're still limited to about 15 frames a second. You go to some analytical formulas, there's some other approaches that they're even lower than that. So that's really one of the killer bottlenecks. And if you break down the architecture here, these upfront convolutional layers, this is where most of your computation time is happening. About 99% of the time for VG16, which is an example of one of these, is all up front, these first few convolutional layers. And if you look at the very first ones, they're mostly these little edge filters. It looks something like this. This is the kind of processing going on. So it's really rudimentary operations. And that's what you're spending all of your computation and power, time and power, both performing. And so this is something that we'd like to tackle with dielectric metasurfaces to do. And so we want to actually take those upfront edge filtration kind of operations and put that into the optics, and kind of make of think of it as a hybrid optical and digital neural network. And so it'll let you offload digital into the hardware optical, which requires no power. You're literally doing processing at the speed of light, so there's no more lag in your system. You're reducing how many components you need and all the algorithm development, and potentially it's compact. You don't need a 4F system, which I'll talk about in a second. And because you're using a dielectric metasurface, you potentially have access to other information channels that you would not readily have access to, such as polarization and phase, some spectral discrimination, etc. This is building on some foundational work in Jason Valentine's lab at Vanderbilt, again, that I work very closely with, where I guess 2 years ago now, he was able to demonstrate this in a lab. Here I show an example of some biomedical imaging he did. I think this is a pig ear he did for the the medical school there at Vanderbilt, where the typical bright field kind of image acquisition of these cellular samples. You can't see anything. You have to go on the back end and do all the edge analysis to figure out where your cellular walls are to do some kind of diagnostics. And you can readily look at this. You put it onto a objective of a microscope here, you can readily see all of your cell walls very quickly. And so it's helping to speed up the throughput of their sampling there at the med school. And even more recently, through a DARPA program, he's been tackling alphanumerical computation. So here we do some handwriting recognition of the number 5. He shows here as an example. So it's kind of pooling all these different capabilities that we've been building the last few years and bringing that into a potentially fieldable system that we're going to slap onto a long wave camera and go see how these actually perform. And so doing optical processing is not necessarily something new. So the idea in of itself is not really novel. They've done this for years back to the 80s using optical correlators. It's a simple optical correlator here, but part of the issue with this is you need a 4F system. You need 2 lenses and put a special filter right here in the Fourier plane in between these 2 lenses. But there's even some other work done in the late 80s. I detail a few different designs here, but even in the simplest case that they were able to achieve, you still need at least 2 lenses and a filter. So you need multiple optical components. You need a really good alignment along your optical axis to be able to do this. And there's some hardware difficulties implementing something like this in our type of case in the DoD. And so the idea is to actually mimic this kind of operation, kind of taking some lessons from freeform optics, but doing that without actual freeform surfaces. And we do this with dielectric metasurfaces. And you can make a full, what we call meta-optic. So this is a proposed flat optic-based design, a single optical element, all embedded onto one piece of hardware that you can put onto your imaging train that has both the filter and appropriate lensing to form an edge-discriminated image. So that's the hypothesis. So for anyone in the audience that's not familiar with dielectric metamaterials, they're effectively composite materials. We're using some kind of sub-wavelength structure that's engineered in some way to elicit a response. It's not unlike the plasmonic particles that I talked about earlier. This is kind of a subset of some of that. In this case, we're using dielectrics, though. So we're leveraging existing lens materials. So it's compatible with everything. It's pretty easy fab because you can go do all the good dielectric fab pretty easily, any kind of silicon fab, silicon nitride, etc. And so if you take a look at this kind of periodic ordered array, it's comprised of many unit cells that you refer to as meta-atoms. You can tune all kinds of stuff to elicit some kind of unique transmission, phase delay, etc. And the idea in the terms of a meta lens here is that you can tune the kind of the local volume fraction of these elements, going from a high refractive index of these really large pillars, it's mostly all silicon dioxide. If you have really thin pillars over here, you can go to a lower effective refractive index. So basically you have spatially varying refractive index, and it's a way to do all kinds of flat lens elements. So you usually would need a curved surface to do, but we can do this in a quasi 2D thick layer. And you can play other tricks with certain meta-atom geometries to, again, get full wavefront control and manipulation over phase, polarization, etc. And so we have shown this in the lab. Again, this is a particular case of just throwing the appropriate metasurface filter on top of an existing lens for proof of concept, where you see some of the experimental done some bar targets, some calculations, and you see they go through this, and here's the experimental measurements. So we know that it works. But part of the issue with this in terms of making a fieldable system is that all the existing prototypes rely on the assumption of a coherent signal. So this was done with lasers. It's not exactly what we see on thermal emission profiles in the actual field. And so the fields are uncorrelated, so no longer can you make a metasurface that's engineered for a particular amplitude transfer function or transmission. We need to go to an incoherent illumination design because that entire operation breaks down. So an incoherent illumination, like we see in our infrared imaging systems, the fields are uncorrelated, and that requires engineering the optical transfer function, which is Fourier transform of the point spread function of our optical element. And so we're moving to actually engineer point spread functions of engineered metasurfaces to get the same operation but for incoherent based illumination. So we know any kind of output image is, again, the convolution of your scene with the point spread function of your lens. And so the question is, what is that point spread function you need? And so if you want to perform the second order derivative, to do edge discrimination, you need to be able to perform the Laplacian of your scene. And so we've been doing a lot of work, actually using a grad from this program, Brandon Swartz, if anybody happened to know him, was a recent graduate last year in Jason's lab. And we're doing lots of AI, ML-based work, as well as some other aspects to figure out how best to design this kind of spatially varying metasurface to actually passively perform the Laplacian of a Gaussian. So you need a point spread function that looks like the green line here. And that's not necessarily something that's trivial to do. So it's requiring a lot of efforts. But we have at least made some proof of concept measurements on it. It does work. Some caveats we're kinking out right now, but I hope to be able to talk about that hopefully in a future time. So just spoiler, it does work, but we're getting to that point of it being publishable. I would briefly like to go ahead and acknowledge all the collaborators that work with me on all these projects. I cannot do all this myself, so everybody from Tim Morgan in the audience, Dr. Sammy Koutsaris back at Crane, all the smart scholars we have scattered at WVU and Vanderbilt, all technical leadership, including John Dilger here in the audience as well, and Stephen Sproul, and all the collaborators everywhere from University of Arkansas, Vanderbilt, Penn State that work with me on a lot of these other concepts. It's not possible without all of them. So briefly, I'd like to touch on collaboration opportunities that we're seeking. We've already had a lot of these discussions since yesterday with many of you, so it's a little bit late coming. But we're always happy to assist in mentoring students, helping test, transition any of your tech that we can do and bring it up the technology readiness level and do some field testing at Crane, provide that kind of feedback loop of what works, what doesn't work in a fieldable system. Career opportunities, if anybody is interested in benchtop optics, getting on an optics table and really building some good systems for us, we'd love to talk to you. You can reach out to me to get contact with anyone here on this list in terms of areas of interest. So, I've talked a lot about more the nanophotonic materials type size today, but we have other interests in quantum materials, AI and data science, radiation effects, spectrum warfare, optics and photonics, space designs for novel detection, directed energy. So if you have interest, just let me know. I can put you in contact with those appropriate people at Crane. And for any students that would like to engage with us, so we have a number of different engagement programs and opportunities. We've talked with you again many about this already. Everything from the student employment program, revolving application funded through ONR called the NREP Summer Internship. SMART obviously will fund scholarships to complete your bachelor's all the way up through PhD level for guaranteed job on the back end if that interests you, and so we're happy to sponsor any students on that. And a more recent program that's been stood up by the National Security Innovation Network, INSIN, is the X-Force Fellowship Program. So if we can come together and maybe have some targeted programs that can target exact expertise and workforce here, we're happy to scope those projects out and take on other 10-week internship opportunities. These are effectively foots in the door. Some have long-term career transition paths directly into Crane. Others might be indirect. So if you just want to dip your toe in the water without the long-term commitment, we're happy to scope those out as well. So if you have any interest, please reach out to us and let us know. And with the summary, I will just leave this up here to take any questions on the back end and just leave this up here for your review. So thank you for your time and happy to talk. Yes.
Hi. Oh, hi. Oh, hi. I don't know if you can talk about it, but can you talk about what kind of optimization strategies you guys are using to construct the Laplacian? Be a set that performs the Laplacian?
Right now we're using just basic gradient descent-based approaches. But as anyone that's worked in that, you'll know that it's very finicky in terms of what your beginning data points are, how that gets optimized in terms of what's spitting out. One of the largest issues with that is actually getting the bandwidth. It's not so much the operation itself that can arrive at a good design really quickly, but on any fielded system, you need to be able to take advantage of the full bandwidth of your imaging band, and that's actually a really hard problem for some of these designs to undertake, so it's a lot of care. But right now we're using a basic gradient descent type algorithm for it. But we hope to go to higher level types of design approaches. There's some new software packages that we've acquired recently that'll have some other approaches we hope to take advantage of.
I enjoyed your talk. It's a really good talk. On the mid-wave stuff, you know, the VISTA program did the Type 2 superlattice work for a while. And I think the temperature of VISTA's up to like 130, 140, or, you know, it's still not room temperature or anything. But I was just curious what your, I mean, do you think that the quantum structure, like superlattice type thing, do you think they'll continue to increase in temperature, and will they become room temperature? Or?
I'm not going to say they won't because my expertise is not in that area, but I have not seen data come across my desk showing lots of improvements in that. I haven't seen if they are making strides beyond the current. I think they're at 150. I think the last time that I saw.
They may have hit a limit or something.
Yeah, so they may have hit a fundamental limit based on the types of barriers that are energetic barriers that are in that superlattice. And so I know that he's done some work trying to go to a PVP-based structures to actually collect electrons instead of holes. As a different material system, but using the same concepts applied in a different material to see if that could actually be used to make that even higher. So we are considering taking lessons from those other things that have been learned over the years and applying them in new materials. Yes?
So what can you say about the sort of assured use dimension of these focal-plane arrays?
We need to make sure that they work. And that they work the way we want them to work. That's about all that that's it.
Oh, okay. I was interpreting that there was something on the slide about directed energy and somehow being resistant to some form of illumination.
Yeah, that's some of the scope of the work that they do there, but that's nowhere that I work personally, so I really can't speak to a lot of the actual science behind it, but that's some of the things that they're concerned with.
I guess are the devices really nonlinear in power in terms of response? Do they have there a range of
I don't know.
Okay.
That's a good question. Honestly, I don't know because I don't work in that space. I would like to make sure something that I propose works before I get to the assured use part. I want it to function first up. I'm stuck at that level right now. Now there's some designs I know that like I played with trying to mitigate some of that. Like I have a plasmonic design of a totally different architecture and material system that outside of the band of operation is a perfect reflector. For instance, like built-in type stuff, but concepts, I don't know if it works. So that's never at the forefront of my designs at this stage.
Yeah.
This might be an overly technical question, but I'm just curious as to why you have sort of an additive rather than a subtractive design for the atomic crystals. Why not poke holes rather than grow pillars?
So in terms of making like for the dielectric stuff.
Yeah.
As far as I'm aware, that would make the reflectivity of these things go up, so we'll lose an immense amount of signal to that. I know there's a lot of work's been done, at least on metal films, poking holes and seeing that transmission is greater than what it should be, but it's still, the absolute values feel very low. So if you take lessons from that and apply it to this case, I still think you're going to lose a lot versus a more air-type dielectric environment. So the whole thing is making that unit cell the effective refractive index it sees and controlling what that ratio is. And so I guess if you want to do holes, it's not too much unlike having lots of almost overlapping pillars and you have little holes in the center. It's kind of like that, but it may depend on what band you're working on, if that would ever actually be advantageous.
And are these test structures, I imagine they're rather small, are there limits on how big you can make using transverse dimensions, or can you make 4-inch wafers of these materials?
We're making wafers right now of these Oak Ridge's system for doing that. So we're making them on at least 2-inch wafers currently. It's big enough for all the optics that we've been using. The individual structures themselves are sometimes several microns, so that they're rather big. Because once we make the initial mass, we move to photolithography from there on out, so we can pump them out pretty quickly. But we've never made anything less than really micron type scale for the most part. So, and when we put that into our code, when we do our design stuff, we constrain the code to look at dimensions that are only easily manufacturable at really good fidelity. You don't want a pillar to kind of look like some kind of weird, octagon, kind of looking. You want a really nice smooth surface. So we make it to so that's purposely simple.
Given that the example you showed was a classification test with the VGG network as your benchmark, current energy costs. With the Laplacian kind of optical front end, what kind of performance boosts are you looking at, assuming you were able to achieve?
We are going to experimentally measure that. We're not at that stage in the program, but we're hoping to get at least 10x improvement in frame rate. And I know, like with the alphanumeric recognition, they're still seeing 96% correct prediction of what that digit is. And so with the current stuff, and that's all done in SWIR, it's not been done on a fieldable, like long wave system like we're looking at. But they're still seeing with the hybrid networks, 96+%, correct categorization, recognition, etc. But we're going to go beyond that, also still measure if we actually get the performance, frame rate gains, as well as power. So we're expecting at least 10x, but that's year 2, year 3 of the program. This just got off in the last 8-9 months, so still at early stages.
Okay.
More questions? I'd like to thank our speaker and also give you a certificate of our appreciation. Sorry guys, I gave a talk.